Okay, hello, welcome back. This is a continuation of the first part of lecture 4 of the intensive course on categories and modules. So lecture 4, the first part is about Yoneda's lemma, and after we finished, we were going through the videos again after recording them, and Basayovic suggested a nice example that I could have given, so I'm recording this extra segment to give that example. If everything was completely clear first time around, then of course you should skip this. But in case not, perhaps this will help. It might be useful to go through this part, to go through this example before the example with manifolds. This is simpler than the example with manifolds. Okay, so thanks Bas for suggesting this example. So let me just very briefly recall the statement. So I'm assuming that you've either just watched the last video or you have the notes in front of you, so I'm just going to briefly write it down. So the Yoneda's lemma says the functor, so C is any category, the functor, which is normally called H, which goes from C to the functor category, is fully found. And what does it do? Well, at least on objects, it sends C to hom, C blank little c, is fully faithful. In other words, it induces a bijection on the hom sets. So this thing we're going to want to refer to, I'm going to call this fun for functor category just because it takes too long to write the whole thing down. Okay, so this is the lemma. Fully faithful, remember, is a sort of categorical version of injective. So what I want to do is I want to give a proof of this in the special case where I take C here to be, big C to be the category of sets. Now this proof is going to be in some sense a bit silly. It's not well, I'll give the proof and then I'll discuss it. So proof in the special case, C is equal to set. I'm sorry that the board here is not fantastic, but it's what's available at this point. And I'll try to write big enough that things are still legible. Okay, so I haven't written down what this functor does on morphisms, which is actually all we care about for fully faithfulness, so I'll talk about, but I want to write it down more explicitly now. Hi, Bas. Okay, so let C1 and C2 be sets, and we have a map, which I'm going to call psi, which goes from hom in the category set C1, C2 to hom in the functor category H of C1, H of C2. Okay, so it's going to send, so what does it do? Suppose we have a map F from C1 to C2. Then it's going to get sent to a natural transformation. Notation for natural transformations, it's always a bit hard to write down because remember, there's a lot of data in a natural transformation. For every object of set op, which is like an element of set, for every object of set op, I'm supposed to give a map from H of C1 of that set to H of C2 of that set. So this is kind of clumsy notation, so it's sort of hard to have good notation, but let's try to write something down. Say for every set E, we're going to send, and for every map G from E to C, so E to C1, we're going to send this to the map, the composite. So this is G, this is F. So in other words, I can write this as G goes to F composed with G. So as I've written it here, this, if you only recently met natural transformations, the way this is written here might be kind of perplexing, but the thing which is confusing is just the definition of a natural transformation. So if this is sort of confusing at first, then you should go away and like stare at the definition of a natural transformation, and then I think you'll realize very quickly what's going on here. Okay, great. So that's our map. We want to prove that psi is a bijection. Want to show psi is a bijection. So this psi is just a map of sets, so we don't have to worry about proving it's anything more fancy than a bijection. So injectivity is sort of, in some sense, the easy part, so I'll start with that. And then we'll move on to surjectivity. I'll maybe make a little more space in the hope that I can leave that on the board. We'll see. Maybe I should stand, if I stand on a chair, I get a bunch of extra board space, so let's try that. If I fall off the chair, we get an amazing video. Okay, so injectivity. Okay, so let F and F, well I should say let C1 and C2 be sets. This is a fancy way of saying let C1 and C2 be sets, so it goes. Let F and F prime be maps from C1 to C2. I'm going to assume that psi of F is equal to psi of F prime. And then I want to show that then F is equal to F prime. And that tells me exactly, of course, that psi is injective. So over there, so if you look at the definition of psi, what I'm going to do is I'm going to make a careful choice of my set E and of my map G. So let E be a singleton, a set containing one element, I don't care what it is. And so, what happens? So let X be any element of C1, C1 is just a set, remember, and define the G from E to C1, and I'm just going to send star maps to X. Of course, there's no other element of E to send anywhere, so that's enough to define what's going on. Okay, so now we know that psi, you can come over here a little more, psi of F equals psi of F prime. Hence, what we find is that F composed with G of star is equal to F prime composed with G of star. Again, I'm just unraveling the definition on the right-hand side here. But this is just F of X, and this is just F prime of X. So what we said is, what we showed is that for every X in C1, F of X is equal to F prime of X. Now, F and F prime are just mapped to a set, so that is enough to tell us that F is equal to F prime. Okay, great. So now I want to move on to surjectivity, but I really don't want to erase the definition here, so what shall we do? Well, I can start writing a little lower on the board. No, that's a terrible idea. Let's write a little lower on the board. So surjectivity. So surjectivity is a little bit more complicated. Remember surjectivity of this map psi. So I'm going to take a natural transformation here, and I'm going to construct a map between these things, which will all get sent to it. Now I'm going, because this part of the argument is a little bit more involved, I'm going to cheat a little bit. I'm going to take something here, construct a thing here, but I'll leave it up to you to check that it actually gets sent to the right thing. Okay, so let's continue my analysis here. So the proof of surjectivity, let the capital F from H of C1 to H of C2 be a natural transformation. Remember that by definition, natural transformations are just the morphisms in the functor category. In other words, I could just say let capital F be an element of this set here. Okay, so we're going to build a map little f from C1 to C2. So we want to build f from C1 to C2 such that psi of little f is equal to capital F. That's exactly, I'm just restating the definition of surjectivity, which is a little bit silly. I think you guys know that by stage in your mathematical careers. Okay, so I'm going to build this map by saying what it does on object. So and what I'm going off the bottom of the board. Yeah. Because I'm not quite sure how low down the camera goes, let me instead hop up here. I'm just going to quickly erase this part. I know you're all watching on videos, so maybe you don't mind if I erase in illogical order, but it seems it could potentially be annoying. Okay. So I'm going to define this map little f. So let x be in C1, I'm going to have to tell you where to send x. So I'm going to do the same thing as before, so let E be the set containing one element, and let G from E to C1 send this one element to X. So then f of G is a map from E to C2, and this star goes to something. I guess I could call it, well, it doesn't matter. So f of G is a map from E to C2, and I'm going to define little f of x to be f of G evaluated at star. Okay, so in this way, for every little x in C1, I have to find myself f of x, which is an element of C2. So I've certainly now written down a function little f from C1 to C2. So an exercise for you. If you feel like doing it, is to check that psi of little f is equal to big F. Okay, so modulo that check, this concludes the proof. So before I conclude this segment, I just want to make a few little remarks. So this proof is sort of very hands-on. We just do it in sort of by pushing around elements of sets. And generally, when one's doing category theory, I mean that's sort of not the, what do I want to say? This kind of proof is not going to generalize so well. This kind of proof depends on all of our objects really, well, I don't know. We're really moving around elements of sets, and that's not going to work in complete generality. And moreover, this proof that I've given here, maybe a more relevant point is that this proof I've given here is not going to generalize all that well. The key thing is really in this surjectivity part in particular. So here to define our map little f on sets, we've only said what our map does on, well. So I guess, yeah, the issue here is, so in the other example given in the main lecture, instead of taking big C to be the category of sets, we take it to be the category of topological spaces. And we could try to follow the same recipe through here to prove surjectivity. If you do that, then what you'll find is that for every capital F here, you can build indeed a map of sets between your two topological spaces. But there's no reason why that map should be continuous. And that's essentially because this test object, this E we've used, is too small or too boring. This E is just a one element set, so it cannot see the topology. So when you want to make all this work for manifolds, you really need to take this set E to be sort of something bigger, something that can really see the topology. Okay, if my rambling at the moment doesn't make sense, then don't worry too much. The last thing I want to do is very quickly is to give a hint for how to do surjectivity in the general case, because I feel that this example we've given here is in some sense a bit misleading. You'll really struggle to turn this into a general proof of surjectivity. So a hint for proof of surjectivity in general. So by in general, I mean when the curly C is not just the category of sets, but when it's any category. So what you want to do is you follow the same approximate structure. You start with the natural transformation, capital F here, and you want to build a map from C1 to C2. And again, we're going to take an E, but now this E is more interesting. So take E equals C1, and take G to be the identity from E to C1, or from C1, I just said E to C1. So then f of G is a map from E, which is equal to C1, to C2, just by definition. Okay, and so define little f equals big F of little g. Again, of course, there are some things to do to check that, so we still need to check psi of little f is equal to capital F. But, okay, I think that's, yeah. So this proof is much slicker, and the proof that I'm sort of sketching here is much slicker than the one I gave for sets, but equally I think the one I gave for sets, you can really see what's going on a bit more. You really see what happens to all of the elements. Okay, so that concludes this bonus section on Yoneda's lemma.